Oh, g'day champions. Over 5 years ago, I did a video on this series of amplifiers. It was very half-assed. I just had a mobile phone up on a tripod in the old garage. You normally hear the relays kicking in and out. That's these two black things over here. So we've got no pad here at all. It's just burnt shit. That's the trace that goes down over there. And it sounds like I have a delivery. So I'll be back in a minute. Embarrassingly, that's become one of the most popular videos on my channel. So I think it's time for an update. Now, the reason that video is so popular is because there's so many of these amplifiers out there in the world, all over the world, and they all eventually have the same issues, and people go looking for answers. Now, Fender could fix those problems if they wanted to, but they don't. They just keep making the same amplifier year after year, decade after decade with the same issues. And it's better to jump on these issues before you start having symptoms from them, because the amount of labour and stuffing around to fix it up increases exponentially the longer you leave it, because they are heat-related issues primarily. So I'll run you through the problems, how to address them, and just general maintenance stuff that you should do to any amp if you're doing a service to it, and just things to generally be aware of in this model, and well, the Blues, the Hotrod, Deville, Deluxe, and to a lesser extent the Blues Junior. I do have a dedicated video for the Blues Junior, so I'll put that in the description below. It's a little bit different from these bigger brothers. These all use similar boards or the same boards throughout the years, and they have various different components populated for the different models. Alright champions, so as soon as I turn around, the inspection begins. Just having a look to see if there's any breaks in the back panel. You can see the valves down there. You have a look to see if they've got any vacuum, if the getter's still intact. One common thing that happens on these, you've got two jacks right next to each other. One of them is for the external speaker, that's the one closest to the valves, and one's for the internal speaker. If you plug into the external, it's a weird circuit on this one. You get no signal because it's an extension speaker, so it's relying on the internal speaker to be plugged in at the same time. Otherwise, you get no signal at all. It shorts out to ground, so there's no threat of a flyback event, providing that jack is in good condition and the shorting contacts are operating as they should. So I like to remove the screws by hand, just so you can feel if anything's cross-threaded, if there's any stuff stuck in the head of the screw. You got to dig that out before you can get the screwdriver in there. It's all stuff to be aware of. Now, sometimes these backs are sort of jammed in place. If you pull too hard, you might snap it at the weakest spots. Sometimes you've got to back the end screws off a little bit because the chassis pulls the cheeks of the cabinet in and sort of holds the back captive, so you've got to back them off before the back can be removed. I've removed this recently for testing and for inspection, so it's reasonably easy to remove. There's also a foam tape which goes rather sticky. They put that there to stop any vibration against the back panel. But it has the effect of sometimes preventing the grounding of the shielding. So that's another thing to be aware of. And it just goes sticky over time. Kind of gross. Alright, so just carrying on with our inspection, having a look for any evidence of arcing, anything like that. Let's come in with a closer view. Alright, so having a look at the left already, we can see evidence of overheating on this resistor which supplies the foot switch supply. It's basically a dropper resistor. It overheats its solder connections. You can see the discoloring there, and it does damage the traces on the other side, but we'll have a closer look at that when we flip the board over. Right, so working our way along, another thing to look out for is the negative temperature coefficient thermistor. Its job is to limit the inrush current when you first turn the amp on. Because it's a relatively large mass item, it can sort of resonate along with the frequencies as you're playing it, and can break its leads off at the base. So just check that they're intact. Of course, if that goes open circuit, you won't have any power because you'll have an open circuit in the primary of the power transformer. Right, now I'm sure you guys have heard about the IC caps, Illinois capacitor branded caps, and how terribly shit they are. Fender just keeps using them because Fender's Fender. They just want your money and they want you to go away. These seem to be even worse than you can possibly buy off the shelf. When you buy them from DigiKey on Mouser, they seem to be a much higher quality than whatever deal Fender got on these. Fender must have really clamped them down to price because they are the worst capacitors in the world. Every single one of them fails. It's just a matter of when. You can see it's leaking its goo out. The electrolyte leaks out, evaporates, drips onto other components, drips onto the board where the HT is, because that's right above the output valves. It's really bad. Fender could stop using them if they want. It's ridiculous that they still use axial caps in this day and age, even in their current production models. So these have to come out and get replaced with a quality item. At the moment, I am using Tube Amp Doctor because I have an account with them. You could use the MOD brand F&T, although in my opinion F&T are getting more expensive every year. But anything's better than these stock caps. They have to go. And you can see right here, this one's dripped, and it's dripped right onto the bias pot. All it's smooth, so that could be compromising the bias supply as well. Now the next part we'll move on to is, again, they could have fixed this 3 decades ago, but they just refuse to. They keep making the same amps that last the warranty period and not much longer. There's probably lots of people out there that have a perfectly functioning one of these. It's pretty old. You've got to sort of take into account that, yes, just because something is a common failure doesn't mean every single amplifier ever manufactured is going to have the exact same failure. We're talking a bell curve of failures in around the 3 to 5 year mark. These generally have a 12-month warranty. I've seen them fail as early as like 3 months out of warranty. It depends how often you use them, how often they're left on, how hot the output stage bias is, because that obviously temperature rises up from the valves and heats this whole area. You've got two 5-watt resistors which are snug on the board, short leads, and they are heating the solder joints again and destroying the circuit board in that area and lifting in the traces and cracking their solder joints on the other side. Not only that, but next to it you've got the two 5-watt Zeners that are doing the same thing. They get very hot during operation and do the same thing. They degrade their solder connections. So these 4 components that need to be replaced, the 2 power resistors and the 2 5-watt Zener diodes, they are a means of regulating a bipolar supply to supply the foot switching circuit as well as the reverb send and return. Now there are ways to do this much more efficiently, like a linear regulator. That technology's only been around since like the late 60s, early 70s. It's not like they've got any excuse for not using it. It would have been cheaper to do and generate way less heat, wouldn't be a problem. But Fender don't want your amps to last a long time. They want you to keep buying amps. That's the name of their game. So they're not interested in fixing this. As long as it survives warranty, they'll keep doing it like that forever and ever, amen. You can see down there on that filter cap, there's electrolyte dripped down and dried on it as well. Where does it end up? Right there on the high voltage traces and the output valve pins. That wire shouldn't be squashed down like that either. So the next issue is the very low quality circuit boards. Both the main board and the valve board are single-sided, very thin traces, very small pads, and very thin copper. So a slight bit of vibration and you end up cracking all your solder joints, and if that happens on like the control grid pin, you've lost your bias supply, you can have a runaway bias condition. And that can cook your valves. It can, if you put an oversized fuse in it like musicians are wont to do, you can cause all sorts of collateral damage as well. Now generally the radial caps in these aren't too bad. Whatever terrible materials or techniques I see used for their axials seem to not be the case for the radials. So you can leave them in for the sake of a couple of, $2 caps. So while we've got the board out, I like to upgrade them to some nice, like 5,000 hour, 105 degree Nichicons, something like that. A brand we can trust. Any of the cons, ironically, Jamicon, Nichicon, Nippon Chemicon, they're all fantastic. Panasonic, even Worth Electronics, pretty much anything but IC is pretty well trustworthy. Stay away from the off brands like Lelon. Fender used Lelon for a while, of course, the other off brand. They're just cheap. They want the cheapest possible parts because they're making so many of these amps. If they can save 50 cents on this amp and they make 1 million amps, that's a lot of money. So the next issue, which is quite common, is the plate load resistors for the preamp. They use these, they look like 1/2 watt carbon films. I don't know if they actually are. I don't know what brand they are, but they go open circuit all the time or very, very high resistance. So I replace all of them with either 1/2 watt carbon films, Yagio, or like Vichy metal films are another good choice if you want super low noise. These aren't massively high gain amps, so we don't have to stress too much about the noise introduced by using carbon film resistors. That can be an issue on very high gain like metal style amps. And it appears on this revision they've added some coax to go to the first 2 valve stages. It looks like a factory modification here. They've used some coax instead of using the ribbon to go to the first 2 triodes. I haven't seen that before. It looks like factory because it's very neatly cut and it's the same coax that they use for all the other stuff. And there's some corresponding cut traces down there on the PCB. So maybe they started experiencing some oscillation issues. I don't know why after all these years of this amp being basically unchanged. They decided to change that at some point. Maybe it's issues they've had with some valve suppliers, not sure. Now, another thing I do, which isn't necessarily a repair, but nice modification, is I change the value of this first stage bypass cap down to like 4.7 microfarad. You can go 2.2 or something. It just cleans up the overdrive, makes it less flabby, less farty, a bit tighter. The next issue is these input jacks are terrible quality. They've got bugger all thread, and it's pretty fine thread. It's pretty easy to over tighten and strip the thread off. It's just that plastic fine thread. Being circuit board mounted too, they often crack their solder joints. So these are the tall type. I like to replace them with some switchcrafts that are mounted to the chassis if we can. The older revisions you can't do it because the jack style is more like a cliff style jack where it's too close to the circuit board to be able to mount a switchcraft. It just can't fit. It's the same issue over here with the effects loop, which is essentially the preamp out and power amp in is forming an effects loop in the foot switch input. But they get used a lot less often, so it tends to be less of an issue as it is with the input jacks. Another thing to be aware of with Fender is every time these handwork, they're not very good at soldering. So that connection there is barely holding on. Yeah, it just came loose with a bit of a probe with the pliers. So that's no good. That's a speaker connection, so we're going to have to clean that up and resolder it and inspect all the others because now none of them are trustworthy. So you've also got the same problems with the plate loads on the phase inverter, but they're mounted on this board, so we've got to remove that board for access. Look, you can try and work from the top, but I've found it's a lot easier and you risk less of a risk of damaging any circuit board traces if you actually remove the board to work on it comfortably. Another thing to check is that the shorting jack is working correctly. Around this area they bunch the cables up. Sometimes cables get stuck in the way and the contacts can just get fatigued. So when nothing's plugged into this, it should default to this jack, but sometimes the contacts fail. And that's when you risk having a flyback event. However, there are flyback diodes in this model, so they should kick in and protect the output stage. The other stuff I've seen too, they put like a drop of like nail polish on the bias adjust trim pot. I guess during shipping they think it might vibrate and move, but what happens is when you adjust the bias, now there's a bit of the track that has nail polish on it. So you adjust it and then you literally lose bias supply in certain ranges. That's seriously dumb. They should stop doing that. If that happens, to address it, you pretty much got to replace that trim pot, and they're not cheap either. They're kind of a weird old school massive thing that you can't find anywhere except specialist suppliers. I just don't know why Fender keep using this ancient stuff. They should move with the times a bit more, I think. I used to have problems with the relays that go intermittent, but they've switched to Omron, which are a good quality, actually reasonably expensive relay, the G6A series, and it hasn't been an issue since. So they're spending money in some places, just not others. Alright, so let's get started in pulling this thing apart. There's probably other stuff I'll think of while I'm going. I'm just trying to remember everything off the cuff on a video, but you know, my brain is not the most efficient at the best of times. But as I think of stuff, I'll just mention it. Now I will remove the chassis in this case. In a pinch you can work on them in place if you're in a bit of a hurry or there's only a few areas that require attention. Pretty much all the things I've mentioned will be an issue at some stage or another. It just depends on the amount of hours the thing's been switched on for and what bias points it's been operating at, that kind of thing. The biggest threat to these things is modders, so people trying to turn it into something that it isn't. Incompetent other techs, and just massive abuse and neglect from the customer. They often come in full of, you know, cockroaches and just dirt and dog fur and stuff, so cleaning them is usually the biggest task. This one's actually in remarkably good condition, so they've got a cover and it's been well taken care of, so it's good to see. You should really respect your gear. I think it's a bit sad when people don't. A lot of people would give their left nut to have this amplifier, so you know, treat it with respect. Alright, so I like to remove the screws on one end. Got to remove the reverb cables. I like to just take the whole tank with it so we can listen to that while it's on the bench. And it's good to inspect the connectors and stuff because they use the world's lowest quality budget RCA cords on these as well. So they're another point that you've got to inspect. The pins like to snap off and they just lose their tension because it's made from very, very thin metal. So this has had a Weber speaker installed, which is cool. They're really nice speakers. I'll inspect the plug and the connections on the speaker. That looks good. It's a Leam branded plug, well soldered. It's an actual speaker cable, not a guitar cable. I might clean up those solder connections, but that's just me being me. I'll just pull the tank out. Try not to let it hit the magnet because it scares the piss out of you every time. And then I like to flip the amp up on the end that you've just removed the screws from. Then continue to remove the rest of them. Just have a quick look at the tank and then disconnect those cables. Alright, so I've got a feeling this one's been replaced because they don't come with an MOD. Usually they've got an Tektronix, but they love to fail, so it's probably already been replaced. MOD are a fantastic tank. 4EB3C1B. So that's a 2-spring unit, long decay, input impedance of 600 ohms, output impedance of 2250 ohms, 2.25k. Input insulated, output grounded. So that is the correct tank. Often other techs just throw in whatever makes a noise without really understanding that, you know, they need to be a specific impedance. So you just got to make sure that code's correct. Each of the letters in that code means something. You can look it up. It's on the Tektronix or Belton website. There's a little chart telling you what it means, deciphering it. We'll just remove it for now. Get it out of the way so we don't drop it. Bag's nice and clean. Often you got to give them a wash because they collect all the dirt and dust in the bottom of the cabinet. Now's the tricky bit. You don't want to rip all the foil off the inside of the cabinet, and often the tabs that the screws go into can be rather tight. So I like to just clamp one side to the bench with a quick grip, and then just force the other side up with your arms as you pull it out. I've got tennis elbow, so it's going to be a bit tricky, especially when I'm trying not to get in the way of the camera. That's come out. No problems. We'll put the chassis aside and then I'll get the cabinet out of the way. But first, while we've got the cabinet out, just grab a socket and check that the baffle screws are nipped up. Was that a 5/16? Yep, 5/16 of an inch. Yeah, they were very loose. This is all part of a service. There's no point getting an amp sounding beautiful if the speaker's going to fall out or it's going to rattle along with every second note you play. Foil shielding, I don't know why they put it on the power side. It should only really be on the input side. It's probably just easier to tell the assemblers to just put it on both sides. While we're here, we'll just check the speaker screws are nipped up. No, they're pretty loose too. Alright, now we're confident the cabinet is all nipped up. We'll stick that aside and get the chassis back on the bench. So we'll just check all the transformer hardware is tight. Just use self-tapping screws on this stuff. It's good to take the thing out, the chassis, instead of working on it in there, because you can inspect everything and see if anything's funky with this wiring or any of the screws are starting to let go or anything's loose or just manky, covered with cobwebs. Gives you a chance to clean it out. Now, of course, we check the fuse every repair that comes in, every service. It's supposed to be a fast blow 1.6 amp, 250 volt, and that it is. And it appears intact, and it is intact. Now we can flip this over and start removing the hardware on the front panel in order to remove the main board. Alright, so you got to remove all the knobs, get to the nuts to remove the pots, to remove the main PCB, because it's all PCB mounted pots, which is nice and fun. But 'tis what it is. That's a requirement for mass-produced stuff to keep the price down. Understandable. People whinge about circuit board amps, but if it's done right, the circuit boards can be the best amps in the world. But unfortunately, circuit boards can also be very cheap. I say can because they can also be very expensive. And because they can be cheap, of course, these companies just love it because they can get the cheapest circuit board possible, get the thing running just outside of warranty, and if it fails after that, yo-yo, you're on your own. But you look at stuff like Friedman, you know, the stuff Jace from Head First is doing. Lots of companies like Tone King make very good circuit boards. Large pads, large traces, 2-ounce copper, good clearance, thick too, 2mm fiberglass thickness. There are ways to do it incredibly well. unfortunately the ones that don't do it very well give all the others a bad name. So if you see anyone just religiously going on about circuit boards sucking, well, it's because they suck and they don't understand what they're talking about. It's not inherently a thing to do with circuit boards. It's to do with how they're designed and what quality they are. I mean, you can get like tag strip constructed amps that massively suck. You can get eyelet constructed amps that massively suck. You can screw anything up. It's not like if you've got a bad design and you don't know what you're doing, somehow having it on a tag strip or a point-to-point construction is going to save you. It ain't. Alright, we'll switch over to the 9/16 socket for the 1/4 inch jacks. The other thing you've got to be careful with these amps is the front panel, the silk screen. Try not to scratch it. Don't use any cleaning products on it. Maybe a very slightly damp rag, but that's it. They get heavily rusted too because the chrome's like the thinnest chrome known to man. So you got to keep them in a dry environment. Don't store them in your garage in a humid garage. Alright, all the front panel hardware is removed. Now we'll just remove the, well, first I'll remove some cable ties because this loom can't sort of move if everything's still tied up. I don't unplug everything. Sometimes unplugging stuff makes it easier. You can generally work on these with most of the stuff still connected to the transformer. Now, of course, I've checked this thing, make sure the caps aren't charged, but we'll just do it again for the pedants among us. 40 millivolts. Better put my rubber gloves on. 40 millivolts. 40 millivolts. It is good to check every node in case one of the droppers has gone open and you've got some charged stuff up the front end. Ask me how I know. Right, now we've got our screws to remove, which secure the board to the standoffs. And somehow my screwdriver's lost its magnetism again, so I'll just grab my super strong magnet, give it a rub, and fly it off the end. Not the most scientific method, but it works. Bam, magnetized. Alright, so we'll just sort of get this board out. Oh, I've got the ground connection to undo yet. Alright, so this one's a good one. With these amps, it's easy to say, you know, oh, why fix what ain't broke? But the earlier you fix these, the cheaper and easier the repair is. So if you've got to start recreating traces and punching turrets through and all sorts of stuff, the costs go through the roof because it's time consuming and every extra part you need has an extra cost and it all adds up. So this one's a pretty good one. You can see the solder joints are starting to degrade, but they haven't gone the full, you know, dark grey, cracked, sort of oxidized look that they will over time. The pads may still have a weakened bond to the fiberglass, so we want to be extremely careful when we lift them and just make sure that we don't go lifting whole traces. If any do start to lift though, don't turn a blind eye. I will put a turret through instead and permanently mount them that way. Generally, once you've done what I'm going to attempt to do here, the heat dissipation is adequate and the damage sort of stops or is slowed down to a point that's about on track with general entropy of the universe. I'm getting into the philosophy again. Alright, so someone's been in here and reflowed these jacks because in the factory they clean off the flux, but you can see evidence of flux there and this solder looks shinier than the lead-free stuff. So that they all look good still, but yeah, we might leave these jacks in place. Just make sure they're well seated because the thread's still in good condition. Like I say, this amp's been babied, but sometimes if there's a lot of damage in this area, you got no choice but to go with the switchcraft. These are the FX loop and foot pedal jacks anyway, so like I say, they don't get used as much as the inputs. But over here, the input jacks look pretty good too, so we might get away with just reusing them. And if it's an issue in the future, we can always upgrade them. Just inspecting all the pot solder joints. It's another place that they love to crack. But they're all looking good so far. I tend to just reflow them anyway while we're here, because I have had times where it's not visible to the naked eye, but there is intermittency, so it's cool to just reflow them while you've got the board out and angry. And over here, that resistor in the foot switch circuit, you can see that that's a bit more advanced. This is what the solder joints start to look like. They sort of go a horrible grey, milky grey, sort of crinkly surface, and then they start to crack shortly after. So the best way to preserve the solder pads on the other side without damaging them or ripping them off the board is to cut the caps off right at the surface of the board on the other side. Sometimes you've got to lift them up a bit to get to the other lead. Camera skill, non-existent today. Now we're left with the little silicon blobs where they silicon the caps down from the factory. That's a good thing to do. We'll redo that, but I'm not re-siliconing to existing silicon, so we'll remove what we can. Just got a very sharp chisel. Just get under it if you can, and try to leave as little behind as possible, without slipping and putting a hole in your hand or cutting cables or slicing off silk screen. And likewise for the power resistors, actually more so here, you got to be very careful because they could have been exposed to heat. Very gently cut them from this side, and then we'll remove the remainder of the lead from the other side very carefully with tweezers. Same goes for the Zenas. We'll cut them off because the new ones we're going to put on, you're going to have longer leads and they're going to be spaced from the board, so there's airflow as well as just allowing the heat transient of the lead itself, because the lead does work like a heatsink. It won't be as hot where it enters the board. Right, now because we can't access the leads under the radial caps, we do have to desolder them from the other side. I'm a bit lucky because I've got a desolder gun, but I'll show you how I would do it if I didn't. Get a bit of solder braid, add a bit of solder to it as well. I use flux braid, which is kind of a must. Don't try and use unflux braid, or you'll just cause all sorts of damage. Now the leads are still bent over, so I like to straighten them up so we've got less of a risk of them damaging the board on the way through. And there we go. You shouldn't have to force anything. They should just pass through basically under the weight of the cap. You can see the little kinks they put in them to hold them in from the Panasonic or whatever machine assembles these things. I don't think they're assembled by hand, they're probably automated. But this is the way I do it because I'm a fancy boy. Got my Pace SX100 solder extracting gun with the station. Alright, now where I've removed the capacitors by cutting the leads on the other side, I just get a little bit of solder on there and then just extract the lead with some tweezers just very carefully. And then I remove the excess solder, inspect the pad, it's looking good, I think we'll be fine. As for the possibly heat affected ones, same deal. Very gently lift the old remainder of the lead out, then remove the excess solder. And that pad has stayed put and there's no evidence of it lifting, so happy days, good stuff. So the reason I add a bit more solder is because I want the flux out of the solder. Trying to do anything with solder that doesn't have a film of flux on the surface is just a waste of time. It oxidizes as soon as it hits the atmosphere and it won't flow. So if I do that one, you can see it's all milky. In this case we're only removing a little lead, but if you were trying to get that to adhere to anything, it's a bit of a nightmare. See, it's gone all crusty and milky, whereas where we had the flux it's all shiny. Well, that's what the flux does. It prevents the surface from oxidizing and basically forming a layer of dross on the molten solder. I found that lead-free solder is particularly bad. The leaded solder isn't quite as bad as lead-free, and there are lots of different formulations of solder and alloys and flux and you name it. So some are better than others. Some are only really good for manufacturing, like automation, and some are meant for handwork. Alright, champions, so here's the parts all laid out. We've got to prep the leads and stuff yet, but we've got our high voltage filter caps there. We've got the two radial caps that were housed right next to the heat generating components, so I like to replace them by minimum. You can go with 470 ohm 5 watt wire wound resistors. I use the V-shaped ones because they're nice and lightweight. These are 7 watt, a little bit higher rated than required, but I've run out of 5, so the customer gets a free upgrade there. The extra surface area will help dissipate the heat more efficiently, so no biggie there. 5 watt Zener diodes. These ones have pretty thick leads. There's a few different shaped diode bodies. These are the slightly fatter ones. I forget the codes, DO40 something, whatever. But we'll prep these leads on the heat generating components, and we'll put a kink in them to anchor them against the board and offer some mechanical support. Here's the metal films we're going to use for the plate loads, and then we've got an 82K for one half of the phase inverter there on the main board. So we've got 400K plate loads for the main board, and we've got 100K and 182K for the the phase inverter, which is mounted on the valve board. Now, while we've got the valve board out, I like to replace these screen grid resistors. The ones on there are fine, but I like to install ones lifted off the board. So if you ever do have a screen grid short, which is quite common, you'll not burn up the board in the process of these resistors overheating and fusing. Now, I do have a funny little video showing the different failure modes of the different composition resistors. Metal film generally fail pretty gracefully, especially if they're safety rated, which these ones are. They sort of work like a fuse, so they don't get too hot before they blow. And carbon film and carbon composition have pretty dramatic ways of failing, so go and check that video out. It's listed in the description below for a bit of a laugh. So let's start prepping these leads and we'll get these components installed. Now, to prep these resistors, I fold the leads over. These are the 7 watts, so they're pretty long. You fold them right over at the body. The 5 watters, you probably want to stick a screwdriver in there and have just a smooth curve. And then I've got these pliers. Now, don't ask me where to get these because I don't know anymore. They were pretty common back when I bought them, but they seem to be a bit harder to find now, and they're offered under various different brands. But essentially, they put a little kink in the lead like that. That makes it sit hard against the circuit board and offers some mechanical support, so you're not just relying on the strength of the glue holding the copper pads to the board. Now, we do the same thing to the diodes. These leads tend to just offer a nice little curve. If you don't hold them right at the base, just bend them like that. And I like to always put them so the value's facing up, so next tech can tell at a glance what component values they are. Then again, I use the little forming pliers there to form a kink in the lead, and then that will sit nice and snug against the board. So all these parts add up to about 25 bucks Australian. Don't buy the overpriced kits that you find online. I'm not going to mention any names, but I think you know who I'm talking about, where they offer basically all of this for about 200 bucks. Not to mention inappropriate components where the leads don't fit through the boards and they just like orange drops that don't fit, that kind of thing, and they promise, you know, that it's going to be a world-changing tone afterwards. More often than not, people try to install those, damage their amps and boards in the process, and then the amp ends up here and it costs them more to pull it all out and do it properly. So I'll put the link to all these components in the description below so you can get on and buy them for a reasonable price instead of paying the snake oil salesman their pound of flesh. We've got no time for that shit on this channel, champions. We just buy from the primary suppliers, the primary vendors. Interestingly, a lot of those suppliers that supply, you know, the mod kits, they don't even include the Zenas, so they're only addressing half the problem, and they're throwing parts at you for stuff that doesn't need fixing anyway. They're basically just hoping that you don't know any better, you don't know where to go to look for the parts, so they end up ripping you off as a result. So I'm here to show you the better way of doing it and the way all of us techs do it, and actually can turn a profit, and you end up getting charged less than going through those snake oil salesmen anyway. Alright champs, our board's got all the silicon cleaned off, everything's prepped, all the solder joins are clean, we're ready to repopulate the removed components and get it back together. So starting with the plate load resistors, I've got a little lead forming tool here, which is handy, just changing where it is on that little conical bit, changes, you know, the amount of lead that's folded over. Just get them in the original holes and just lightly bend over the bottom side about 45 degrees, ready for soldering, so it holds the component in place while you flip the board over, and then rinse and repeat. Alright, here we are with everything dry fitted. You can see the diodes were already pretty sturdy before we even soldered them. A little bit more play in the resistors there, but everything's pretty tight, and once we solder them, everything will be locked in. It forms like a little anchor on the other side of the board, but more importantly, we can't push them down any further, and they're spaced off the board because of the little kinks in the lead that we put in with those forming pliers. So that's what allows airflow around the components, allows them to convectively cool, and also isolates them from the actual board itself to prevent any more heat damage occurring to the fiberglass. We've got our new Nichicons here, just got to replace this one now, and then we'll flip it over and solder them all. Alright, so just prepping the leads for the filter caps. Again, put the logo facing up for the next guy, and I like to just get a nice smooth curve just around my forefinger there. And roughly line that up with the holes in the board and just check you're not miles off, and we should be good. So being somewhat large and massive items. I put a dab of silicone just in line with the leads, not much, just a little dab will do you, and that's enough to just prevent any vibration from potentially cracking the leads or the solder joints in the future. Now they are polarized, so you got to get your polarity correct, or you'll soon know about it when it explodes on first power up. Again, we'll just push those leads over at 45 degrees, get the rest of them in, and then turn it over and solder all the connections. Now on the Hotrod and Blues Deluxe, you've got some links and some unpopulated components, so make sure you put the caps back where they were. You can see the remnants of the silicon from the factory ones, because on the Blues Deville, all the capacitors are populated. So this is like a universal board that they use for the Deville and the Deluxe. And in the Deluxe you've got some unpopulated components and several links and stuff where on the Deville they'd be populated. Alright, so that's everything on the main board ready for soldering. So let's flip the board over, we'll solder them, and then we'll reinstall this board and start working on the other one. Now I'd just like to use the quick grip again, just gently, like not much tension on it at all, just to hold the board there to counteract the spring of the cables that we have disconnected. Alright, so now I like to sort of hold the component down as I solder it. I'll get the solder happening first, and then once it's molten I just hold the component against the board while the solder sets, and then do that on the other connection as well. And the standoffs make handy little solder reel holders. So you must have a temperature adjustable iron. This is a pace with a MBT station. Don't be using any hardware store irons that don't have a temperature control or unregulated temperature, because they will just fry everything. The amount of these amps that come here with people using hardware store irons, you can permanently destroy the board or make it so the repair will be very costly, because you're going to have to put turrets and run wires and everything to repair the damage. So I'm sitting at about 320 degrees, which is more than adequate, using leaded solder. If you use lead free, you might have to lift that temp somewhat. Just get the pool happening, then reach down underneath, just make sure it's seated hard against the board, and burn your finger in the process. Now the diodes with their fat leads do take a little bit more heat to get happening, so I like to heat the lead a little bit before coming down on the pad, just to prevent any heat damage to the circuit board if avoidable. I try not to sit on the capacitor connections for too long, because they are heat sensitive, particularly with film capacitors. You should really either use a hemostat as a heat sink, or just be very quick and only have the temperature as high as you need to. Of course, having the temperature too low can also cause you to sit on a joint for too long, and that gives it enough time for the heat to go into the component. So sometimes not having a hot enough iron can actually work against you as well. It's sort of a sweet spot, and I found on my iron, although it's not calibrated, I've got a pretty good feel for it now. On the iron it's set to 320. Not sure exactly what temperature that is, but it feels perfect to me. Now you don't want blobs of solder, you want like a nice fillet. You want it to be sort of concave. But there's whole articles and everything on soldering, which we might get into one day, but it's outside the scope of this video. Alright, with everything soldered and secured against the board, I just go through and trim off the excess of the leads now. And then we'll just clean up the flux, try to make it look like we haven't been here. Sort of like camping, you know, you leave no trace that you've been there before. If it looks factory, you've done a good job. In this case, it's going to look better than factory because it's a Fender. So here's a slightly earlier one. It's got all the same issues, pretty much, well, very similar board. The only difference is it's got some different jacks here, which require a 5/8 nut driver. You're a nut driver. And you can see here there was a dedicated coax position on the board. It looks like on the more modern one they've tried to get away with just using the ribbon connector, no coax, and then they've realized that that leads to some performance issues, so they've gone back to coax on the new one and had to cut traces and stuff to make it happen. Just a classic case of trying to cut corners a little bit too far, realizing it compromises performance and having to go back to how it was before. But yeah, all the same issues on this one, heat related stuff. This version they've actually tried to do similar to what I'm doing and lift the resistors off the board a bit, and they've put 2 dobs of silicon there. I don't think that's reworked. That looks like it's from the factory. The customer said this has never been serviced, so we'll do the same treatment to this one after we finish the first one. You can see the different brands of relays there. Like I mentioned on the new ones, they've gone for Omron, which is good. And you can see how close those jack barrels are to the PCB, which is why you can't use the switchcrafts on this version. Now when I'm soldering, I didn't have it on before just so it was nice and quiet for the video, but I do have a fume extractor with a HEPA filter, purpose designed for soldering. You can do it anywhere well ventilated, like in a garage with you know, an open roller door or something like that's probably adequate. You can get small desktop fume extractors, but I found just having a fan in the general area to push it away from where you're working is adequate. It's not the lead that's the issue. The lead doesn't get anywhere near hot enough to evaporate. It's the flux. So the flux fumes can cause irritation to the lungs, that kind of thing, and possible other long-term effects, so it's best not to breathe that stuff in. And isopropyl is highly flammable, so you can't filter it through a cigarette butt either. Alright, so to clean the flux off, I just like to just get a bit of paper towel, stick it in the chassis, and hold the board over it and let it drip onto the paper towel. As you give it a scrub, I use 99.997% isopropyl. That's the electronics grade, technical grade they call it. I don't like using the stuff from the supermarket, which has got about 30% water. I like to keep water out of the equation if I can. Isopropyl alcohol is hygroscopic, so by the time you open it, the water percentage would have increased to maybe 1%, but it's still better than the 30% stuff that's used for window cleaning and general purpose sterilization and whatnot. Here's the stuff I use. I get it from Tektronix in, I believe they're in Sydney. 5 litres, it's about 30 or 40 bucks. It'll last you friggin' ages. But plenty of other companies sell the same stuff. You get it from like cleaning supply places, that kind of thing. You can also get dedicated flux cleaners, which are a little bit more efficient at the job, but I just like using this stuff around as a general purpose universal solvent. And I have a little pump dispenser, so that enables me to grab the brush, just get a little bit on there, and then scrub the board. So once all the flux is dissolved, well, it's still wet, I just blast it off with compressed air. That helps take most of the flux residue along with it before it dries out, evaporates. Right, so after a couple of cycles of rinsing with isopropyl, the board may still have a little slight milky appearance to it. That's just a tiny bit of really diluted residue still on the board. I just give it a scrub with a dry brush after that, and that just gets off the last bit of it and gives the board that nice dark look again. Almost like buffing. And there we go, nice shiny board ready for reinstallation. But before we do that, we'll just remove the rear board. We'll just try not to cramp our style too much by installing that board. We've got a little bit more room here, so I leave the standoffs on the board. They're sort of held captive by the output valve sockets, and I just remove the screws from the outside so we can approach the board from the component side. To do that, you've got to take off the valve retainers as well, and just set them aside. Just don't lose any screws, champs, because they're a bit of a weird thread. They're probably readily available in America, but in Australia everything's metric over here, so you might have trouble sourcing some replacements. Just keep everything in a container. Don't lose track of stuff. Don't leave it sitting there on the bench, because it will roll off onto the floor and hit your boot and fly across into another universe. So I use the recycled takeaway containers just to hold everything. I usually have one for the old parts and one for the parts that are getting reused, like the hardware. In this case, I just was in a bit of a rush, so I put it all into one container, but you know, we'll fish through it later. Now we don't need to remove the V1 board. We just need to remove the larger long one. Just move that out, just have a quick inspection, make sure everything's looking okay. We've got the negative, oh here we go. So we've got some wires snapped off. Moving this stuff back and forward's not great, but I think that wire was probably already fractured, which is probably half the reason it's come in. But in the meantime, we'll replace this cap, both the plate loads and the 2 screen grid resistors over here. Alright champions, we've got everything installed on the valve board. You can see the screen grid resistors down there elevated off the board, as we did with all the other heat generating stuff. So we're ready to throw this board back in. We've got some carbon films there. I might upgrade them to metal film fusible resistors as well. Just same value, 100 ohm, but just lift them off the board a little bit as well, just in the event that we do have a short from heater to HT. They won't set fire to the board underneath them. There'll be a bit of isolation there. They generally don't dissipate much power at all. So I just put some half watt 100 ohm fusibles in their place. So we'll do that, and then we'll install a board and get to testing the unit. So before reinstallation, I like to twist the anode leads there. Just gives a slight amount of capacitance and cancels out any stray signals that may cause oscillation. You can see down there the little grey wire, that's the negative feedback. I just steer that below that bottom post down there. Alright, so when tightening these plastic threaded jacks, I just like to use the socket, just friction in my hand, to prevent stripping the thread. If you put the handle on, you're tempted to put too much torque on, and that will damage the jack, requiring a replacement. Alright, champions, so this is just a bit of a flex, showing off on my Flukes. This one I'm going to use for just probing around voltages. This one's measuring currently the DC resistance of the primary of the output transformer on one side, and on the other side you can see there's a fairly big imbalance there, almost 30 ohms. But what matters is the turns ratio. So what often occurs is the internal windings have a shorter distance to travel, so they'll have a lower DC resistance, but the same amount of turns, so they've got the same impedance. So impedance is like, think of it in very basic terms as AC resistance. We're using the DC resistance in this case to measure the voltage drop across it, because at the static or the quiescent operating point, we want to know the amount of current that the anode is dissipating, and that's what we're going to use to bias this thing. There is a cathode current sense resistor, a 1 ohm resistor installed in the stock circuit, and that's what they tell you to use to bias the thing. But I like to just check balance on this, because that cathode resistor is shared between the two valves, so it doesn't tell you anything about how imbalanced these are to each other. And the cathode current will also be including the screen current as well, which is another couple of milliamps, whereas we're directly measuring the anode current using this method. It's a bit more dangerous. I suggest using the factory method and the service manual, which is readily available online, to get in the ballpark. But this is I assume other techs watching this are already aware of this method and use it, because you don't have to install anything or use bias probes. You can just use a standard meter, and just be careful. And over here on the right we've got the B+, so that will jump up through the roof, and then as the valves start to conduct, it'll drop back down to its normal state. So first I'm going to use a variac, just bring it up to a couple of volts, and just check that we've got negative voltage, and we've got the same voltage on all the HT nodes, and just make sure we haven't done anything silly. I'm going to watch the wall power consumption meter. These are great. They're like $30. It's a good little safety measure. You can measure the amount of power consumption from the wall, and tell if anything's running away, or if you've got any short circuits, that kind of thing. That will go through the roof at very low settings on the variac, and you know something's wrong. As much as Dad likes to make fun of me for using my variac instead of just going straight for it, the day that you don't use it is the day that you'll regret it. Alright, champions, so we'll flick it on, stand by and the power. Slowly bring up the variac, keeping an eye on the power consumption meter. We're sitting at about 40 volts and it's only drawing 7 or 8 watts. Bear in mind this has a sort of energization power of about 5 watts with 6 watts with nothing plugged into it. I'll just run the meter across all the relevant points and check for any weirdness in the voltages. We've now got 112 volts on the B+. The output valves won't be conducting for some time. We're not at a level where they would start warming up yet. So we've got the same voltage there. Because there's no current yet, because the valves are cold, there will be the same voltage on all the plates. So we can easily go through and just check that everything's as we would expect. Okay, just have a look at the bipolar supply over here. The input exactly 12, minus 12. And 12, plus 12. And on the regulating side, we've got minus 7. And about 7, 6.7. So that's nowhere near where we want to be, but point being, it's pretty balanced and we've got the correct polarity, so that's good. Have a look on the grid stoppers on the output. Check that we've got bias, yep, minus 11.3 on one side, minus 11.3 on the other. So we've got bias supply to the main board, that's good. The output valves are just starting to conduct there as they warm up. You can see 10 millivolts and 6 millivolts. So we'll bring it up since we've got no catastrophic issues going on. I'm feeding it with a 1 kilohertz signal. We should start to get some signal as the output valves start to conduct. Only drawing about 20 watts from the wall so far. 240 volts on the plates. And there's our signal. The relays won't be switching yet until we give it a bit more. Alright, now we're at about 200. Only drawing 45 watts. We're we've got what feels like pretty healthy signal. Channel selecting is working. There we go. That's switching between the master volume and the clean channel. That switch is a bit sticky. I'll have to give it a clean. Bit of a pop there. So I'll just check that there's no DC anywhere where there shouldn't be. We could have a leaking coupling cap. Right, so that's sitting around 200 volts, and I'm happy there's no short circuits or anything crazy. So let's power that off, and we'll just give it the full 240 volts now and see where we're sitting at with the bias. So while we're in standby, we'll just adjust the we'll check the trim pot that there's no dropouts from the aforementioned glob of paint and electrolytic from the cap above it. Seems to be good. We've given it a clean. I'll just adjust it so it's most negative. You can see on the left hand meter back there, minus 54 volts. So that will be dissipating the least on the valves, providing everything's in good shape. Alright, you can see there it's sitting at 435 volts on the plates, 1.6 and 2.6. So that's although there is quite an imbalance on the DC resistance, that is quite a bit out. Right, so we've got 1.6 on the left hand side. So I'll just grab a calculator. I'm not smart enough to do this in my head. So 1.6 volts divided by 81 ohms equals 19.75 milliamps. Multiply that by the plate to cathode voltage of 436. So 8.6 watts. Divide that by 30 because it's 6L6. We're running at 28.7%. So we can work backwards from that. Say we want 55%. 55% of 30 watts. Go 30 watts divided, multiply by 0.55. 16.5 watts we're aiming for. Divide that from, estimate that'll sag quite a bit, probably to say 425. So we'll estimate, divide by 425. So we want 38.8 milliamps. Now to figure that out in terms of volts dropped across 81 ohms, we'll multiply that by 81. So we want 3.14 volts roughly on the left hand side. And on the other side we're aiming for 16.5 watts as well, but we're dealing with different resistance of 108 ohms. Divide that by 425, which is our expected estimated plate voltage. So we want 38.8 on that side as well. Obviously that's the same as the other side, but now we multiply that by 108 ohms and we want 4.19, say 4.2 volts. So we should be seeing about 3.1, 3.2 on here and 4.2 over here. So let's see how far off we are. You can see the voltage starting to rise. Right, we're already at 4.2 on the right and we haven't made it to 3.14 on the left. 3.15. So if we go halfway between the both, say about 3 on the left, 4.35 on the right, that's averaging 55 between them. Let's actually calculate it. So 425 is a good estimate. We're at 426 volts. So at 426 volts, we've got say 3 volts on the left hand side, 4.35 on the right. So on the left, 3 divided by 81 ohms equals 37.0 milliamps multiplied by 425. We'll reduce a bit, 422, because we've got to take off that, we've got to subtract that from the overall. I'm just measuring the B plus here, not the direct plate. There's just too much stuff in the way. So B plus minus this voltage is 422. Multiplied by 422 is 15.62 watts divided by 30 equals 52% dissipation. Now for the right, we've got 4.35 divided by 108 ohms. That's 40.3 milliamps multiplied by 421. Subtract the 4.3 off 425 approximately. Equals 16.9 watts. Divide that by the maximum dissipation of 30 watts. Equals 56.5%. So we'll add 52 to that. 108.5 watts, divide that by 2. Our average is 54.25. Close enough for the girls I go out with. So that's almost bang on 55%. Let's see how that compares to how they tell you to measure it in the service manual. They want to see 60 millivolts on the 1 ohm cathode resistor. So let's see where we're at. It says bias test point in the copper on the PCB. So that we're at 90 millivolts. So that's 90 milliamps shared between the two, including screen current. So if we adjust that down to the specified voltage, which is not taking into account, I might add, the plate voltage. They're just telling you a flat current on the cathode, so it's not actually a dissipation measurement. It's not taking into account the plate voltage. But let's just do it and see where we sit. Alright, we're at 60 millivolts on the cathode, which over a 1 ohm resistor corresponds to 60 milliamps. And I have checked that it's a 1 ohm, still within tolerance. Now we've got 1.9 and 2.9. So 1.9 divided by 81 equals 23 milliamps multiplied by 432. 10 watts divided by 30, obviously 33.7%. So they're telling you to bias this thing at around 30%, which is pretty damn cold. So I might bring it up back to where we were, so about, let's go 50%. Alright, so now we're sitting either side of 50%. We're at about 48.5 there and about 52% here. So we've averaged these two valves. They're not a perfect match, but like I say, close enough for rock and roll. So everything's stable in the output stage. Let's do some listening tests and just establish everything else is healthy and working as it should. I've already heard a million of these things, so I can tell instantly if something's not correct. Damn, I was hoping I could use this as a teachable moment, but it's not quite bad enough that it's giving symptoms. Yeah, I was hoping to show you some crackling from these cracked solder joints. It's on the phase inverter valve, so I wouldn't have done anything dramatic. It just would have been popping and crackling and stuff. But yeah, inspect the solder joints on all of the PCB mounted sockets. These are terrible quality PCBs. There's no through-hole plating, so the only mechanical support is this little fillet of solder around here. And as you see, they've got little circles around them, which shows they're about to crack. In this case, it's not bad enough that it's causing issues, but it will in the future given enough vibration. And I should mention that, well, I've got any of these circuit boards out, I do inspect every solder joint. I run an eye over the whole board just to find things like this, but I was just hoping to show it as an example later on, but no such luck. Anyway, we'll power it down, we'll touch these up, and carry on. Alright, so there it is with the solder joints cleaned up and reflowed. You can see it nice and shiny. Not a big blob. Having a large blob on there doesn't do anything to help. It just hides any potential issues with the solder joints. So you still want to fill it, but the amount that they put on from wave soldering in the factory is quite minimal, barely adequate. So just a nice healthy fillet, nice and shiny with no little rings visible. You can see the difference compared to what it looked like beforehand. Alright, so here's my dummy loads. I just got them screwed to the wall under the bench, and that's 8 ohm, and you can arrange them in either 16 or 4 ohm as well. There's two 8 ohms there, so you can wire them in series or parallel. In this case, we're just going for a single 8 ohm. So let's measure the output power. Alright, so we've just got a 1 kilohertz signal going into the scope. You've got the voltage reading up there to the right. It is flickering a bit due to the refresh rate, the frame rate of the camera. But we're leveling off there at 17 volts RMS. And it's a pretty healthy looking waveform. No crossover distortion or any weirdness. You can see the top and bottom just starting to level off there, and you can actually see the ripple occurring. So 17 volts, let's calculate that. So 17 square divided by 8, 36 watts RMS at the onset of clipping. So that's pretty average for these. They say they're a 40 watt amp, close enough. You got to take the power output measurements for all these companies with a grain of salt. They tend to just round up or down, usually up to the nearest figure, just to make it more effective marketing wise. 36 watts is plenty, and this thing would sound very powerful and healthy by the looks of that waveform. So let's have a listen. Just checking the heater voltage, and as is often the case, mark of the beast. So I haven't done any real voicing changes in this other than the bypassing the first stage. There's whole swaths of stuff you could do to these amps. This is basically just to get them up and running again. The reverb circuit in particular could do with some voicing changes, but you know, that would be a dedicated video. So I feel like I've paid my dues on these things. The first couple of years of getting into repair, this is pretty much all I saw, these things, and Blues Juniors and all the classic 30s, that kind of thing. I'm starting to get some nice vintage gear now, but these things kind of got me where I am, and I got a little bit of a soft spot for them, as annoying as Fender are for building in all these faults year after year, decade after decade. And one last thing before we put it back in the cabinet, the screws on the end of the chassis tend to bend this little lip outwards, so that makes it very hard to get it back in the cabinet without ripping all the foil off. So I just like to gently bend that back with what we call a shifter, in the States known as an adjustable wrench. You guys and your funny accurate terminology. And just do the same on the other side as well, so it doesn't rip the foil off the cabinet as we insert it. Don't bend it too far though, because you'll risk cross-threading those inserts and they're a pain in the ass to replace.